All right, so we're here with Barry Bond. You're an architect. You specialize in emulation.
That's
so
right.
Tell us about yourself. What do you do?
Well, right now my current project is the device emulator. That ships as part of Visual Studio 2005
Okay.
and is set to ship with an upcoming release of Windows CE. The device emulator is basically an application that runs on your PC that emulates a Pocket PC or a smartphone or a Windows CE based device.
Okay.
Gives you the full development experience that you would expect as if you were targeting a hardware device, except it's all local on your machine in Windows.
So let's talk about that for a second. So is it kind of like a virtual machine? So you're virtualizing, the target hardware, right? Is that what you're doing?
Like a virtual machine. For the purists who are looking for the dictionary definition, the device emulator is a software simulator.
Okay.
A virtualization is where you take the real hardware that you're running on and you share it between two operating systems.
Okay.
With the device emulator, it's quite different. We're running an ARM-based development board, which is what we emulate, on top of a PC. So different processor, different motherboard, different display, different input, everything. So the device emulator is closer to Word running a VBA macro than it is to something like Virtual PC, which is sharing one PC with multiple versions of Windows running on it.
Okay, understood. So let's talk a little bit. So that was good. Let's talk a little bit more about emulation and how you do it. Like what's going on. So let's talk a little bit about the ARM emulation, as you just mentioned.
Okay. Behind the scenes, the device emulator is taking your ARM instructions, JIT compiling them to x86 instructions, and executing the x86 code.
Okay.
We JIT compile for performance because most instructions get disassembled and JITted once and then get executed multiple times for loops and big structures and programs. We emulate a motherboard. It's basically the Samsung SMDK 2410, which is a development board that runs Windows CE. It's a fairly generic Windows Mobile or Windows CE device, has all the things that you would expect, has a touch screen, has an LCD display, has 64 megabytes of RAM, it's about 200 megahertz device, has NAND flash, NOR flash, PCMCIA slots, serial ports, all of the bells and whistles you would expect from a device. And we emulate all of that to the level where you can build Windows CE for the Samsung board, take the ROM, and load it in the emulator and it runs.
Outstanding. And even though you may be developing on, 4 gigahertz, 16 core machine with 10 gigabytes of RAM, that doesn't matter because you're masking all of that, and you're
Right.
Otherwise it would kind of be silly.
Right. So we present you with the window on your PC, which looks like a little Pocket PC or smartphone or Windows CE device.
Excellent.
The performance is close to what you would get from a real hardware device running CE and Windows Mobile, 200 megahertz to 300 megahertz. The emulation overhead costs us a lot because we have to emulate not only just the ARM instruction set, but all of the things that make ARM interesting as a processor. It has alignment faults, it has page sizes that range from 4K up to 1 megabyte, sort of lots of things that make ARM different and unique that are actually important to software developers. If you're writing your code on x86, alignment faults are not something you experience. The processor takes care of them. On RISC processors like ARM, if you have an unaligned pointer, you're going to get a crash in your application. So the device emulator is a very high fidelity emulation of the ARM environment. It isn't just running the instructions, it's memory protection, alignment faults, all of the things that ARM provides.
Outstanding. And so you mentioned JITting. So you wrote this written in managed code?
No.
Or, I mean, I know that. I want to clear that confusion up.
Yes. So the device emulator is written mostly in a mix of C and assembly code. I fear I may be one of the last people at Microsoft still writing assembly for a living.
Wow. Here he is, ladies and gentlemen. Amazing. All right.
Dinosaur from the coding era of assembly code. But inside the device emulator, inside Pocket PC or Windows Mobile, we can run anything. JScript code, .NET CF1 and 2, Java, Flash, it doesn't matter to us. Those are just big pieces of ARM instructions, and it doesn't matter where ARM instructions come from. We compile them from ARM to x86 and we run them.
Okay. And so, I mean, it would be difficult to write an application for a Pocket PC on a Pocket PC. Yes?
Right.
Right, Visual Studio Pocket PC Edition.
Never put the toolbars onto the screen.
Totally.
Right.
So, I mean, this is clearly necessary and important.
Yes. So the way you develop for Windows Mobile today is you use Visual Studio 2005 on your desktop. Visual Studio 2005 has smart device projects for C#, VB, C++. They bring up forms designers that are skinned and sized to look like Pocket PCs and smartphones, so that you can lay out your controls on a Pocket PC or smartphone. You can test rotation, you can change screen resolutions, do all of those things in the forms designer. When your app is built and you're ready to test, press F5 in Visual Studio to compile and deploy your app. Up pops an emulator on the screen.
Okay.
So now your app deploys into the emulator, and you can actually run your code and see it running.
Excellent.
The interesting thing is that you can launch the emulator, deploy your app into it, and it's a clean state emulator. It isn't like taking your Pocket PC or your phone out of your pocket, cradling it with ActiveSync, where your Pocket PC is polluted with your contact list and your ringtones and your applications and things. You have this nice clean development environment in the device emulator. You can soft reset it or hard reset it. You can launch any one of the 10 or 20 emulator images we have for different screens and form factors and operating system versions.
Okay.
So you don't need a huge suite of hardware devices to deploy and test against. You can deploy and test on the emulator to do most of those OS configuration kinds of testing.
Cool. Now, when I'm developing an application for one of these devices, if I try to do something that's sort of out of the range, the intelligent range of like memory utilization or whatnot, the compiler or something's going to tell me that while I'm in the IDE. So, or do I have to wait for the emulation to crash?
Right.
Okay.
So the development experience in Visual Studio has IntelliSense that's scoped to the APIs you would expect on the device. So for native code, we use IntelliSense based on the Windows Mobile SDK. If you're writing managed code, we use the .NET Compact Framework metadata to drive the things that you can use. But in terms of figuring out of memory, that you have to run your application for real to go see what your memory footprint is.
Okay. Now, can I debug? So when I go into debug and you pop up the emulator, I can step through my code, and then if some fault happens, I can, in the emulator, then I can actually go and debug it. I mean, clearly you have the debugging interaction.
Right. The device emulator, as far as Visual Studio is concerned, is just another device that Visual Studio can target.
Okay.
It can target devices over ActiveSync, it can target over Ethernet, and it can also do a very high performance point-to-point connection to the emulator. But as far as debug and deploy, it's the same whether you're emulator or device. You have the full native debugger, the full managed debugger, single step, breakpoints, everything that you would like.
Fantastic. Cool. So, we covered the basics of emulation. I mean, we could get down to some gory details if you want. What does assembly code look like anyway for those people out there?
Oh, goodness.
You want to write some assembly code?
I can write a little bit of assembly code if needed. I still ask it as an interview question every so often. I know assembly code in the resume. Great.
Cool. Well, I mean, that brings up, let's diverge a little bit to the human side of the story. I mean, you're an architect, and that title sort of varies from role to role in the company. Clearly, you're writing code, and you're an engineer.
Yes.
You're writing code, but you're also thinking about business implications, interacting with customers. So, how do you define what an architect is?
I call myself developer/architect. I'm a developer first and an architect second. I'm still growing into the role of architect at Microsoft.
Okay.
But I'm very much from an engineering background at Microsoft, primarily doing development. But architecture comes to me with this responsibility to think, sort of multiple versions ahead and multiple products wide about where Microsoft should be going and where the thing that I'm working on should go. So for the device emulator, we actually have a roadmap that goes out 4 versions. So device emulator V1 has shipped. V2, we're at Community Tech Preview. V3 is actually planned and we're starting to execute. V4 is also planned, ready to go. So we're thinking out fairly long term, multiple years about where we're going. But we also think of the device emulator not as just a technology inside the Visual Studio box. It's a technology for Visual Studio. It's a technology for Platform Builder.
Mm-hmm.
But for our customers, it's not a technology. It's a tool to get their work done. It's a tool to be productive. So I'm less interested in what the right algorithm is, more interested about building the right emulator to solve the customer problem. So if you think about Windows Mobile, we have countless display sizes and form factors that we would like our applications to run against. Square, high DPI, low DPI, landscape, portrait. If you think about devices, we have multiple radio stacks to contend with. How do you test your application against all of that? I mean, some devices aren't even available in the United States. How do you build this library of all of these devices to test against? Don't. Use the emulator.
Okay.
Test the bulk of your application on one device, on hardware. Hardware is always better than emulation. But use the emulator to go do all of that breadth testing that you need to do to make sure your app sizes and displays correctly and things like that. The device emulator also takes away as many of the limitations as we could find that get in the way of doing device development. Devices have small memory, 32 megabytes, 64 megabytes. My personal device runs with about 5 megabytes of free memory. So I'm really limited if I want to build an application. If I want to test on my own device, I have to squeeze it into 5 megs. But I'm a developer. I want to write a big app. And I want to write an app that has unoptimized code and assertions and logging and instrumentation and things like that. How do I squeeze it onto a device? Use the emulator. We have 256 megabytes of RAM if you would like it. We have unlimited storage capacity. We can take a directory on your Windows hard drive and project it in as if it was a storage card. So it's live data sharing. If you update a file from Windows CE or Windows Mobile, it shows up instantly on the Windows side. And this is as big as your hard disk. So if you've got an application with big data, or you want to write a log file, keep track of where your application is, the log file can be 1 gig, 10 gigs, 100 gigs, whatever your disk space is.
Interesting.
So if you're used to thinking about living sort of constrained inside a device, running your app on a tiny little smartphone, you can think of it as a tiny little smartphone backed by all of the things that Windows does for you. Big storage, big CPU power, a big environment to run in.
Interesting. Now, one of the things that I'm struck in with, whatever the word is, I always do this. Am I struck with, or something I wanted that just hit me? When I'm running in the emulation mode, if it's actually not a virtual machine and you're not running Windows CE inside of your context, which is a separate issue, how do I really get because I mean, clearly systems are always doing other things besides running your application.
Right.
So if I'm running the emulator, then I'm going to be 100% I'm number one, my threads have priority, nothing else is getting in the way, there's no sort of realistic situation. How do you emulate a realistic situation like that? And do you?
That's a tough one, and we really don't.
Okay.
The device emulator is just a Windows application. We do almost all of our work on a single Windows thread, and it's responsible for doing all of the CPU emulation work. So it's the JIT and the execution. The nice thing with that is that it's scheduled by the Windows scheduler. So if you're doing email, the emulator's in the background. We also try as much as possible to idle the emulator. If Windows CE goes into a while one loop, polling, waiting for some data to arrive, we tend to turn that into a sleep as far as Windows is concerned.
Okay.
So we try to be good citizens. But if the emulator is running, compute-intensive Windows CE code, it will be at 100% CPU on your Windows box.
Sure.
Subject to the scheduling that Windows does for us. In terms of performance and how much bandwidth we get out of your Windows machine, the emulator is basically designed to be best effort for performance. We don't throttle the emulator to run at some predefined speed. We run it as fast as we possibly can. We think for user mode developers, you want your app to run as quickly as possible. It may run faster than it would on the fastest Pocket PC device. It may also run slower than the fastest Pocket PC device. We don't meter our emulation to be accurate. We don't emulate clock cycles or anything like that. Loads and stores instructions in ARM are quite expensive for us because we have to emulate virtual memory and ARM page protection and everything else in software. That's just slow, a lot of operations to do. But if you're doing arithmetic, adds, subtracts, multiplies, compares, and branches, the device emulator can be much faster than a real ARM device. Remember that we're running on like a Pentium 3 or Pentium 4. It probably has a 4 megabyte data cache. It's this giant, big, fat desktop machine. We're emulating an ARM processor with a 32K cache, code and data. So we get a lot of benefits from running on big desktop processors, and we can actually be quite fast at some code.
Excellent.
But our goal is to average 200 megahertz or 300 megahertz of emulation, and with every version we're going to get faster.
Very cool. So, I mean, how do you restrict a cache size for applications running in your emulator? And what does that look like?
Right. We don't actually restrict the cache size.
You don't?
No.
Okay.
Again, that's something that would limit performance. And in terms of our cache emulation, we don't actually emulate one. For the data cache, we just said, all reads and writes are identical. And for the instruction cache, we basically emulate an infinite instruction cache. When we JIT code from ARM to x86, we have almost unlimited storage because we're running on a big Windows machine. Yeah. So we let the cache grow as big as possible. The only time we flush it is when we're in dire straits and we're out of memory, or when the CE kernel asks us to flush the ARM instruction cache.
Okay, interesting.
So if you want cycle-accurate emulation or cache-accurate emulation, device emulator is not the right technology for you. There's some great third-party emulators that do those things, but it costs them greatly in terms of performance.
Okay. So let's talk about that. Like let's talk about the right times to use this device emulation.
Sure.
And then we'll also jump into this interesting thing I heard about shared source emulation project that you've been working on.
Certainly.
But let's begin first. So so for UI and other things.
Right. So the device emulator, our primary customer is user mode application developers.
Okay.
Definitely graphics intensive, forms intensive applications are the most interesting applications to do on the emulator. We support SQL everywhere and all of the rest of the data technologies because to us they're just bunches of ARM instructions. We don't care where they came from or what they do.
Okay.
So if you're a developer and you're interested in developing an application that talks over ActiveSync or over network, pretty much centered on the device emulator is great for you. Some of the things it's not good for is things like developing device drivers in Windows CE. Because our emulation is fast as possible, we're a little loose on exactly how we emulate the hardware underneath. If the hardware underneath, for example, says, do this operation and wait a certain number of microseconds for the hardware to settle, we don't wait. As soon as the emulator can catch up, we report success. So it's not great for timing-sensitive code. It's not super great for performance investigation because we don't make an effort to be accurate in terms of performance. On average, we're pretty good. So if your app seems slow at doing something, it's probably slow doing that on a device as well. But you can't say, I took X milliseconds on the device emulator, so it'll take X milliseconds on a hardware device.
Sure. Understood. Because the overhead of software emulation.
Right.
The overhead that is software, not hardware.
Right. And keeping track of a virtual clock would be sort of a very expensive operation to do without much benefit. So our goal is really like how fast can you, design your UI and put your business logic together and press F5. How fast can we get your form on the screen and how fast can you interact with it? That's the performance that we want to get.
Absolutely.
If you want to go do deep investigation of what the Dcache is doing, then you probably want to go to the ARM toolkit for doing cache investigation.
Sure. Now I can see clearly another use of this would be for ASP.NET developers, right? I want to see what Channel 9, which I'm sorry, Niners, because we have never gotten around to doing this, what it actually looks like on a Pocket PC.
Yes, very much. Pocket PC for the device emulator comes with all of the mobile apps.
Sure.
Pocket IE, you get the whole experience of living inside the nice small form factor.
Cool. So Pocket IE inside of your emulator.
Yes.
What you just said.
You can surf the web. We have device emulator images now that support Windows Mobile 5 with direct push. I actually dog-food it every so often and do all of my email here at Microsoft for a day inside the device emulator.
Wow.
Using Pocket Outlook.
Nice.
It's kind of fun. It's actually a small and pretty fast mail client as mail
Cool.
clients go.
Very good.
So the image comes with a full set of applications that you would expect on a Pocket PC. So
Okay.
it's quite full functional.
So you can obviously use your keyboard then.
Yes, you can.
Right?
You can use the keyboard. We deviate a little bit from the minimum hardware specs by giving you a smartphone with a full QWERTY keyboard with 96 some odd keys on it.
Sure.
But in terms of the rest of the emulation, it's quite close to hardware. One of the important things that we do is we emulate a touchscreen. So touchscreen and a mouse are very different in terms of how they behave and how they appear to applications. Right, a mouse pointer, if you leave it somewhere, it's still there. Right, you come back and look for it later, it's still on the screen. With a touch, it comes and it goes. And so we actually emulate that aspect of input. But other than that, yes, there's the keyboard because we're developers and we like to type. And
Yes.
the on-screen hunt and peck is
Fast.
is too inefficient to get the job done.
Cool. So just out of curiosity, what application do you use when you're writing your code? I mean, you're not writing assembly in Visual Studio.
Yes, I am.
Wow.
I use Visual Studio 2005. I am delighted with IntelliSense for native code. Works incredibly well for me. I'm very, very happy with it.
Okay.
Most of the assembly code is actually not sort of .asm files or inline assembly. Most of the assembly code in the emulator is actually JITted code. So our output is assembly code. We take this ARM code, we translate it to assembly code that's output. So what you see inside the emulator is actually what you would think of as a computer science compiler. It has a parser, takes ARM instructions as input. It has an optimizer that works on the high-level representation. We have a code generator, and then we have an optimizer we run over the generated code. Along the way, we have a ton of C++ macros that piece together x86 instructions into our in-memory JIT cache. And they all have complicated names because we wrote them in C, and it's hard to generate assembly code instructions from C macros. So IntelliSense actually is the great way of sort of getting documentation on all of our crazy macros.
Nice.
So let's talk about shared source.
Let's do that.
Because you can actually go see my crazy macros.
All right.
My crazy JIT compiler.
Okay.
We are very excited to have released the source code to the V1 device emulator as a download from Microsoft.com. It's a petite zip file, about 470K. It is the full source to the device emulator, plus a Visual Studio 2005 solution file that lets you download it. You have to plug in 2 third-party libraries of code that are quick and easy downloads, and you press F5, it compiles, and you get deviceemulator.exe from your own code base.
Fantastic.
So the license is for mostly for academic use. We're very interested in opening up the emulator and letting people experiment with the insides of the emulator. This could be things like instrumenting it for performance. It could be to instrument to monitor Windows CE. For example, you could add a cache simulator inside it and then watch the cache simulation run. You can instrument the peripheral devices. You can add new hardware to the motherboard. If you're particularly enterprising, you can unplug the ARM CPU, plug in a whole different CPU. Anything you would like to do, x86, MIPS, SH4.
Excellent.
The full thing is there. It's modular and sort of set up to be pluggable to begin with.
Excellent. And that's because, in general, you brought up a good point with modularization and componentization. That's bread and butter for mobile development, typically.
Very much so.
Right? You have to actually be very modular.
Yes.
As opposed to like the giant monolithic systems that we are slowly but surely changing over time.
Right. So the device emulator, if you look at the retail commercial version, it's one big exe file, deviceemulator.exe. In fact, for the most part, it's xcopy deploy. You just park the exe on your machine, pass the path name to a ROM file, it launches, and it goes on its way. Don't be confused. It's an exe file because it's easy to xcopy onto a machine. Behind the scenes, it's actually composed of a bunch of interfaces. There's a pluggable CPU, there's a pluggable motherboard. On top of there sit pluggable buses like PCMCIA, and pluggable peripherals on top of there, and a whole UI and graphics subsystem that are separate.
Do you want to draw this out? that be easier for you?
I can give it a try.
Sure. I mean, since people are going to actually, from this video, will have links to your shared source. So now we could use this as a way to just kind of dig into what you're just talking about.
Great. Yes.
It's always nice to look at pictures.
Absolutely.
All right.
Okay. So the device emulator, if we think about it, is a big Windows process. And inside it are a bunch of parts. The parts are actually quite straightforward. There's the CPU emulation. The CPU emulation is a virtual processor. It has a register file. ARM has 16 integer registers, R0 through R15, and it has a couple of status registers and some internal state and things like that. That's all encapsulated into the CPU. And this is a lib file inside the device emulator. And it has some really simple interfaces on it. Start simulation is the big one. You start it, it runs, and it runs until it stops.
Mm-hmm.
There isn't much to it. Plugged into the CPU is the motherboard. And the motherboard is where the RAM lives and the ROM lives. And this is really flash. We have both NOR flash and NAND flash inside the device emulator. If you look at the source code to the emulator, you'll see the RAM is just a global array of bytes. There's nothing complicated about it, it's just an array of 64 megabytes. ROM is equally just a pair of arrays of bytes. There's no particular exciting thing about them. And then attached to the motherboard are a set of peripheral devices. And the peripheral devices are the things you would expect to see plugged into a board. This is the interrupt controller, the LCD controller, the touch screen, all of the things that make up a full-blown Windows mobile device or an embedded device. The way this is all implemented in the emulator is the emulator is a Windows app. So if we want to do interaction with the user or interaction with the PC, we don't touch the PC hardware directly. We always go through Windows APIs, and the Windows driver stack. So for example, the touchscreen is based on some manufacturer's touchscreen hardware, and it takes data as points of input. If you push the pen down on the touchscreen, you get a couple of hundred interrupts per second that have coordinate data in them. We emulate that by calling out to Windows, user32, GDI32, with window messages. So we get window messages, or we get tablet ink information from the PC, and we just get those messages, WMS up and MS down, the tablet events, and we convert those things into touchscreen events. Similarly, for serial ports, we emulate a COM port inside the device emulator. Well, how do we emulate that from the Windows side? Easy. Create file on COM1 : on your Windows machine. Whenever Windows CE changes the baud rate register inside the emulated serial controller, we call Windows setcom DCB, which is the thing that changes the baud rate on Windows on the Windows serial driver. So we never talk with the hardware directly. We always go through NT security. We always go through Windows APIs. So we are pretty much just a Windows application.
Okay.
So inside the source code, you'll actually find C++ classes that implement each of these peripheral devices. And they all have a pretty standard interface that connects the CPU to these peripheral devices. ARM uses memory mapped I/O. So some of the memory accesses are redirected to the RAM and ROM arrays, and some of the memory accesses are turned into read and write methods on these C++ classes. So the emulator has a lot of moving parts in it, but each of the parts is actually quite small. If you think about how you would emulate touchscreen hardware, you look at the touchscreen driver in CE. It's basically a state machine. The touchscreen driver gets an interrupt, it does a little bit of work, it triggers some event inside CE, and it goes back to waiting for another interrupt. This touchscreen emulation is the state machine that plugs into the bottom of the driver state machine. So if the driver expects an interrupt, we'll deliver an interrupt. If it expects some data to show up in a register, we'll put the data in the register.
Excellent.
So there's these little tiny state machines, and we built them up one by one from, pretty much an empty class, based partly on the hardware specs and partly on what the driver sources do. So this is all composed together to be the device emulator. Emulation for the CPU, emulation for the peripherals, emulation for the motherboard, and then basically the layer that's in here is the Win32 interface. This is where our skin engine lives, this is where the mouse and keyboard input live, this is where our menus live, things like that. So this interface is the thing that basically takes the virtualized world and turns it into the Windows world on the outside.
Excellent.
So the other things that are in the process are actually quite straightforward. There's a JIT cache we call Windows Virtual Alloc, and we allocate a big piece of memory, and that's where we store the translated ARM instructions. And other than that, we don't do much. The device emulator, if you think about it, is sort of a pretty simple loop. You fetch an instruction, you execute the instruction, it has some side effects that change the state machines, and then you fetch the next instruction and go. In fact, the earliest device emulator code I worked on was a simple interpreter, and it could boot and run an entire CE operating system for a board, and the most complicated data structures in the emulator were a loop and an array. No hash tables, no trees, very straightforward data structures.
Okay.
So jitting makes it more complicated, getting performance makes it more complicated, but at the basics it's fetch an instruction, run an instruction, do it again.
Very cool.
Run billions of them.
Excellent. Well, that's really helpful in sort of understanding the emulation process and also what people can play with in your source code.
Absolutely.
So I could plug in my own little component. I mean, you have 3 of them there. There might be some other funky sort of user input.
Absolutely.
Construct that I could then program against and plug it into your emulation.
Much. We'd like to see people be able to plug in new kinds of peripherals, whether it's advanced network cards or simple things like a GPS. There's lots of places available to plug new parts into the emulator.
And so now earlier you mentioned that the emulator clearly is in the right place for me to write drivers.
Right.
But if I do want to play around with a new piece of hardware on this framework, I'm going to need to have a driver.
Yes.
And so where would I develop the driver? And how would I test it?
Well, you can. Yes.
I realize that drivers are all about hardware to software.
Right. So you can use the device emulator inside Platform Builder. In the next version of Windows CE, we have a great integration between Platform Builder and device emulator. In the current Windows CE 5, you can go and download the source code to the device emulator BSP. BSP is board support package. It's the layer of code that sits below CE and above the hardware that contains the boot code and the low-level drivers. So we have the full source code of those available. That's the place to go to get started at writing a virtual device driver that ran on top of the device emulator. So you can go there and see what we're already doing. You can definitely write drivers on the device emulator, but you have to have a hardware model to run the driver against. And the fidelity of that model really affects the quality of the driver that you write.
Absolutely.
So if you can code a model accurately enough to satisfy yourself, you can definitely write a driver.
Now, that sort of, again, highlights the difference between emulation and virtualization.
Yes, very much.
Because I could, in fact, write a driver on a virtualized system. Because I'm only given virtualized hardware.
Right. And the hardware model is typically very accurate.
Sure.
So if you think about virtual PC, their hardware model is very accurate because they run a broad variety of operating systems. The device emulator is very focused on Windows CE and the way Windows CE operates, and so it runs Windows CE and CE-based operating systems and pretty much nothing else.
Excellent.
So that gives us both great performance and a much simpler emulator.
Now, could I do things like, this might be sort of weird, but if I just wanted to change Windows CE, like pull out components and add things. Windows CE is very componentized, right? I mean, it's a kernel and then all these things around it that you can pull out and plug back in. So if I wanted to just see what my new crazy shell component is for CE, I could do it in the emulator.
Yes.
Clearly.
Yes, you can.
Cool.
Yeah. So when we're plugged into Windows CE 5, we're just another target board as far as CE is concerned. You can go all the way down to the 1 megabyte min-kern with the kernel and nothing else. You can go up to enterprise webpad and the monster 30 megabyte operating system image.
Cool.
So the emulator is basically just a peer to the existing hardware boards that Windows CE supports.
Excellent. Well, this has been very helpful. And we will. So, do you have a blog? How do you interact with developers out there?
I do. I have a blog.
Okay.
blogs.msdn.com/barrybo, BARRYBO.
Okay.
And I am delighted to answer questions on the device emulator, the shared source version, the BSP for CE5, and anything else emulation related.
Cool.
I'd like to talk about this.
Now, are you planning at all on putting this shared source version maybe on something like CodePlex?
Definitely thinking about it.
Okay.
As usual with these projects at Microsoft, it was important to get the zip file at the door, into the public hands. And then I do want to go back and put it on CodePlex to make it easy for people to collaborate.
Excellent.
The zip file is great for standalone, download and experiment with it on your own. But I wanted to enable people to push things back up and share them. Definitely.
Fantastic. All right. Well, hey, thank you for your time. And this is great stuff.